Hello, everybody. We have now finished the topics of initial value problems and solving them numerically. So we took that all the way from basic Euler's method through to these Runge-Kutta multi-step methods and how to program them. So with that aside, we're going to turn our focus for the next couple of lectures to something else, something that's really important as modern application of mathematics. And it's something that's used pretty widely these days in like artificial intelligence, neural networks, things like that. In fact, it's pretty hard to search this topic without running into these things because it's so big. So we are going to be talking about a topic called gradient descent, and it uses concepts at its very in its basic form that we all know. Okay, it uses first year calculus concepts, and I think that we can gain some understanding by considering what's going on in like one dimension and then extending over the next couple of lectures to more. So hopefully you're able to follow along and get something out of this. Why don't we get started? So gradient descent, back in first year calculus, we used derivatives in order to seek the solution to optimization problems. That is minimizing or maximizing some sort of objective function. You know, we've seen functions like, cost and minimizing cost or maximizing area. These kinds of things that you see in first year examples for optimization problems with respect to a particular quantity, like the spatial dimensions or whatever might be involved in the problem. But sometimes problems like that can be really hard to solve, especially when you have a very complicated equation or something with a lot of different dimensions, right? One thing that I find with calculus students in first year is that doing optimization problems is usually among those topics that is more difficult for students to do. Imagine though that those problems in first year are all single variable optimization problems. How big can a function f be depending on what x is, or how small? What's the biggest it can be or what's the smallest it can be? But imagine for a second that you have an optimization problem with an objective function that has literally 20 variables and you're trying to figure out how big that can be with respect to all of the variables. And you have all of those degrees of freedom. Using basic calculus becomes completely impossible. It's going to be too hard. So we want to find some sort of scheme that is able to help us with those optimization problems, especially if things get rough. Gradient descent gives us a scheme that allows us to locate an extreme point given an initial guess that is, like a lot of things in this course, close enough. So you need an initial guess that's close enough to an extreme point that we can actually find what that extreme point is. And it can be applied to many problems, no matter how complicated or high dimensional they are. Well, okay, I guess that speaks for itself when we talked about before. And this is a scheme that's going to rely on, like the last couple of topics we've done, derivatives. So we're first going to demonstrate how this works, the 1D function, and that's going to be the focus with this lecture right here. So imagine that we had to jump back to a first year sort of one dimensional, one variable example here. We have a function of just x. So we have the function e to the 2x minus e to the 3e to the x. And we have the interval minus 2 to 2. So we're trying to find the minimum of this function on that interval. Okay. I want you to notice this is a function that doesn't skip around. It's differentiable. It's continuous. There's no problems at all with how smooth it is on this interval. Okay. Well, let's see. We can see from the graph that there is a minimum value. It's like right about here, maybe just shy of 0.5, not quite sure. Somewhere between 0 and 1. F, this function, this exponential, this combination of exponentials, this f is our objective function. And we are minimizing the objective function with respect to x. So we want to find which x value makes the least value of the function, of the objective function. With gradient descent, this is how we work. We start with some sort of initial guess. We'll call it p0, x equals p0. We're going to use the slope of f, i.e. the derivative of f, evaluated at the guess to give us information on which direction we need to go to find our minimum value. So here's an example, right? Suppose our P0 is right here. If our P0 is right here, over to the left of this this minimum value, check out what the slope of the tangent is. The slope of the tangent is the derivative at this point. It looks like it's negative here. The derivative is negative, and therefore if the derivative is negative, that means it's going downward. So that means the minimum's got to be ahead. It's got to be in the future. It's got to be at a greater value of x. So my next estimate that I'm going to take is going to be a step forward. On the other hand, suppose if my P0 was defined to be something, say, over here. If my P0 is over here, what we're going to do is I'm going to evaluate, oops, I guess I want the derivative at P0, which would be the derivative at this point right there, which is going to be that. And we can see that the derivative there is positive. Because it's positive, it's coming up, which means it's coming up from a minimum point, which means that if I had to make a next guess, it should be a step backward. And this is kind of how it's going to work. At every single guess that we get to, we're going to check the derivative, we're going to see whether it's positive or negative, and then we're going to step either forward or backward, depending on what the result is, and depending on whether we're trying to maximize or minimize a problem. And that's how this is going to kind of work together. So let's get rid of that. I'm going to kind of reiterate this in the next page. So, as I said, we're going to take our guess, we're going to evaluate the derivative as a first step. If the derivative is negative, the function's decreasing. And that's nothing new. That's just stuff you should know from first year. So it's nothing crazy. It shouldn't be stressful. And because it's decreasing, we know that if we take a small step forward, we should go down. And if our goal is to minimize a function, we're going to get to a test point that's forward. On the other hand, if the derivative is positive, the function is increasing, which means it's coming up from a place where it was less. And so my next guess is going to have to be a step backward. We're dealing with step sizes again, so step size of h, whatever that's defined to be. And we're going to evaluate our new test point. You can't take for granted that where you land is going to be less than where you started, supposing we're trying to minimize a function. Imagine, if I go back up to this example up here, suppose that my x0 was right here, or my p0 is right here. I would check the derivative, I would see it's negative, and then I'd take a step backward, or sorry, the derivative is positive rather, and so I'd take a step backward to get to a next point. If my h is too big though, maybe this is where it takes me, and the function could be higher up than when I started, which means if maybe I've jumped over this minimum point or something, my step has been too big. So it has to be something else about decreasing the step size to make sure it's small enough that I can hone in on that minimum point. That's what I'm talking about. You need to make sure that your steps are small enough. So you evaluate your new test point, and if f at that test point is less than the f of the point you're at, then that means that the test point is closer to a minimum than our old point was. That becomes our next estimate. Okay? If it is not less, well, we knew because of the derivative information that we had to be going in the right direction, so we must have just stepped too far, especially because our function was continuous and differential. It changed smoothly. So our h was too large. And so what you do is to redefine the step size h to be smaller by some factor. A simple way would be to cut it in half and then try again. And you repeat the process until h is smaller than some specified tolerance. So for example, I would say we could cut h in half and then just try again. And if you are still overstepping, you cut in half again, and so on and so forth. So yeah, that's pretty much it. So why don't we check this out? The sequence of estimates we get will eventually crawl around on the real number line until it hones in on a minimum. Backing up to our graph, we can see how this will work without doing any calculation whatsoever. So imagine, right? Imagine if we had, let's try something out here. Let's try if we had an initial guess of p0 equals minus 0.5 and h equals, yeah, why don't we go with 0.5? Okay. So if we did that, then my first guess would be right here. This would be p0. I would test, I would see that the derivative is negative, so I'd take a step forward, and my next estimate would be p1. I can see that the function's lower there, so we did something good, and I would evaluate the derivative here as well. I see it's still negative, so I'm going to say negative, step forward. Here it's negative, so we would step forward. And if we step forward again, we get here, because we're going up by 0.5, so this would be our p2. And if I evaluate there, it looks like it's very slightly negative, or very slightly positive, mixing it up, this is positive. So we'd step backward. But if we stepped backward, we'd be right on top of p1, and that would be higher than where we started, so I have to cut that in half, and I'd step a little bit in this direction instead, and so on and so forth, right? This might be my p3 if it's lower, but it's getting very, very small already. We're already honing in, see, on that minimum value. So maybe this is lower, maybe it's not. I'll put a p3 question mark, but you see how this works. We're using the derivatives at every single one of our estimates to kind of direct us on which direction that minimum is. And eventually, you just get there as closely as you want. And so it's a pretty neat technique. And you can see it working really well here in one dimension. And it's important that we understand how to do it in one dimension before we try to extend it to 2 dimensions or 20, which is, this technique is used for very big problems sometimes, because usually it's pretty easy to work with. Okay, if you don't have the derivative, I just wanted to do a little bit of a note here. From a week or two ago, you could use finite difference approximations if you needed to estimate. A finite difference approximation would let us estimate the derivative if you needed to. But here we're going to work under the assumption that we have derivative information. So yeah, as I said, this is a technique typically used for higher dimensional problems, and finding extreme points can be more challenging there. So the process from the first example can be extended, but we have to take some care. Oh, shoot. So I wanted to do one more. This is going to be my next video. So this is a big preview of doing higher dimensional problems. What we're going to do is go back to that last example. I forgot that we had an example down here. And I said, let's actually do the calculations here. So with an initial guess of p0 equals 0, and initial step size of h equals 0.25, we can actually do the calculations. My apologies. So let's remind ourselves of the problem here. We had, what did we have for a problem? I think we had, it was a couple pages back maybe. Yeah, it's f of x equals e to the 2x minus e to the 3x. Sorry, getting lost in my own notes here a little bit. So we had f of x equals e to the 2x minus 3e to the x. I've given myself some room here. I need the derivative. So let's find f prime of x here. And that's going to be 2e to the 2x minus 3e to the x. Of course, we can calculate this just fine. We have a p0 equals 0 here and an initial step size of h equals 0.25. So first thing we're going to do, I'm going to note how big the function is at the initial point, so 0. So f of 0 is equal to, if I plug this in, e to the 0 minus 3e to the 0. That's going to be 1 minus 3 is minus 2. Okay, and we're going to use that scheme. So let's find f prime at 0. Okay, so actually I'm gonna say this is for p0. I'm gonna just keep a record of where we're at on the side here. Sorry. So p0 is equal to 0, and f prime at 0 is going to equal 2e to the 0 minus 3e to the 0, and that is minus 1. And because that's minus 1, that means that the derivative at 0 is negative, which means that I'm going downward, which means I need to take a step forward. So, let's write down something about that. So negative, we step forward. You can see that in the graph, right? If we were at 0, we saw that the tangent here is negative. We're going to take a step forward. Here we're using 0.25 for our h. So let's do that. What we need to do is we step forward and we want to test f at 0.25. And that's going to equal, if you work this out, you end up with minus 2.203 or so if you put that in the function. And this is less than. It's less than where we were before. So we're going to keep it. We're going to keep it, and we're going to let P1 equal 0.25. Right? We are lower than where we started, and so we're on our way to doing something good. And once we've got established that our next estimate is going to be 0.25, we're going to test f prime at 0.25. And so if you work that out, let's actually evaluate this instead of just writing down a number. How about this ends up being 2 times e to the 2 times 0.25 minus 3 times e to the 0.25, just to let you know where that came from, right? This ends up being about minus 0.5546. So again, it's negative. So again, we're going to step forward. And that means if our step size is 0.25, we're going to test 0.5 for our next value. And if you put that in, you get e to the 2 times 0.5 minus 3 e to the 0.5. This works out to, what did I get here? Minus 2.22788. And notice, so my first estimate here, my first function, right, evaluated to minus 2. And then the next estimate had the function being minus 2.203. The next one's even less than that. So we're getting less and less and less. It's changing less and less because we're getting closer and closer to that true value. And so it's less than minus 2.203. So keep it. And that means that our P2 is going to be 0.5. And we're going to do this one more time. I just had performed some calculations, so I kind of just want you to see how things work and the first time it turns and so on. So if P2 is equal to 0.5, I'm going to test f prime of 0.5. This works out to 2e to the 2 times 0.5 minus 3 times e to the 0.5. And this works out to positive 0.4904. And since this is positive, we're going to step backward because that means we're coming up from a minimum point. And so we're going to turn around and notice that if we were to try out P3, if we were to step backward by h equals 0.25, we would end up with P3 equals 0.25. But that's where we were, and we know that's higher than where we're at right now. So we got to cross this out and redefine the h so it's half the size. Redefine h to be equal to 0.125 perhaps. And try P3 equals 0.1. I'm stepping backward from 0.5, so it's going to be 0.375 that I try next. And if I do 0.375, then I'm gonna test. I'm just gonna do this one more time because I'm almost out of paper here, so that's okay. Um, f of 0.375 equals. I didn't do this one in advance, so I'm bad. So I'm gonna do it right here. 0.375. I need to multiply that by 2. I need to exponentiate that, and then I need to subtract 3 times 0.375 exponentiated as well. And so we end up with negative 0.130. That can't be right. Let's try this again. 0.75 exponentiated, and I'm going to subtract 3 times 0.375 exponentiated. I get minus 2.248. So that is a better estimate. That is less than what we were at. Minus 2.248. See, that was just a moment where I knew I got like minus 0.2 or something on the first try. So I knew, based on what I know about the graph up here, there's no way I jumped up that much. So I had to mess something up with my awkward fingers and stuff. Happens sometimes. But this is less. This is our next estimate. So I'm going to say this is less than minus 2.22788. So keep it. And I'm going to say, and so on. So right now, you see how this works, right? Our next step, we would evaluate the derivative there. We check to see if that was positive or negative. And if it's negative there, we would step forward. If it's positive, we would step backward again. And we're going to hone in as closely as we want to that minimum point. We know the minimum point exists from that graph there, but maybe we don't know exactly what that is. But you see how we can get arbitrarily close by continually chopping the h in half if we need to, and getting further and further better estimates. And this is how gradient descent works. In one dimension, you can see what this is all about. Now, I kind of spilled the beans on this next example because what we're going to be doing is taking this in one dimension and seeing how we can extend it to more than one dimension. What happens if we have 2 spatial variables and we're dealing with the calculus of surfaces and stuff like that? That's tough. Not everybody in the class has a ton of experience with that. So I need to introduce some new calculus for those of you who don't know it, but some familiar calculus if you have taken things like advanced calculus or advanced calculus 2, the concept of a gradient. And it's not that bad, I promise, but we need that before we go forward. So yeah, I got a little bit mixed up in the middle with where we're at, and I almost missed this example, so I'm glad I didn't. But hopefully once we did get into the example, it kind of demonstrated the point. We're really just using data about the function to kind of direct us on where to go next. And our goal is just to kind of hone in on what that minimum point is. And notice, you could do the exact same thing with a maximum point, except you'd flip things around, right? You'd think about what the slopes increasing or decreasing would mean, or the slopes being positive or negative would mean, and whether we should step forward or backward based on that, just on what you know about first year calculus. So hopefully this was a good introduction. We're going to get into that higher dimensional stuff, maybe get to an example in the next video, and then probably do a little snippet on how you might decide to code something like this after that. So I hope you'll join me. Ciao for now. And everybody take care of yourselves and take care of each other. I'll see you soon.